Hello everyone and welcome to this section. I'm super excited to discuss a very important topic in computer vision, which we'll call it Hough transform, okay? And we're actually going to use it directly, the Hough transform, along with what we learned before about region of interest masking, to actually kind of combine them together to come up with a technique that can detect lane lines for us, okay? So Hough transform mainly can be used to detect lines in an image, okay? And let's take a look at what do you mean by an actual Hough transform and how can we actually apply it when in an OpenCV environment. Okay, so a little bit of math. I know, like, again, I promised you not to cover or not to dig into a lot of theory and a lot of equations and mathematics, but I like, you know, there's no way. I have to dig a little bit into the mathematics and show you how can we do it kind of from a very high level into intuition form. So let's assume that I have this line, and my objective here is to model that line. Just get a model that basically tells me the equation of this line. We have covered that before, in basic mathematics, that y equal mx plus b, where I can represent any line as kind of giving me the slope, which is m delta y by delta x, okay, which is the slope of my line, along with b, which is the intercept. How can I be intercepting the y-axis? Okay, all right. Another representation, okay, or another kind of representation of that line using what we call it the rho value and theta. Okay, what do you mean? So let's assume that I have this line, and here I have my origin. I can represent that as the exact same line using just kind of a different equation. Okay, assuming that from the origin, I'm going to draw a perpendicular line to my desired line. Okay, again, this is my line that I'm looking for. I'm going to draw a perpendicular line to it. Okay, I can represent the equation of this line using rho and theta parameters. Okay, what do you mean? So theta is simply the angle with the horizontal line. That's the theta. And rho is simply the distance from the origin perpendicular to the line, which is this distance. So I can represent this line using these two rho and theta parameters. Okay, it's kind of a different representation of the line. Why again, the question is an important question. Why are you teaching me this? I'm teaching you this because we're going to use them to actually kind of use these two parameters, okay, to obtain lines from the image. I'm going to show you how, which is a very, very smart kind of technique that's going to be used to detect lane lines within any image, or not lane lines, any straight lines. I'm going to use it again for self-driving cars to detect the lane lines. All right. So again, rho is the perpendicular distance from the origin to the line, and theta is the angle formed by this perpendicular line with the horizontal axis, from the perpendicular line to the horizontal axis. And this is simply the equation of the straight line, the exact same straight line. I can x multiplied by cosine theta plus y times sine theta. That will give me the rho value. And that's kind of the two equations of a straight line, exact same straight line. All right, let's make use of what we learned. All right, so let's assume that I have my vehicle, and I'm taking a camera image from this vehicle. Okay, what I'm looking for is that I'm looking for the equation, or I'm searching for the line. In order to search for the line, I need to search for the equation of that line. So again, I mentioned the equation of any line, not specifically lane line, just any line, is y equals to mx plus b, or x cosine theta plus y sine theta equals to rho. Okay. All right, so these, in simply put, what we have just described is what we call it in the image space. So in the actual image, I can represent the equation of the line using one of these two equations, okay? However, instead of using the image space, I'm going to use what we call it Hough space, which is a different kind of representation of space, okay? What do you mean? So each line in the image space, so this line in the image space, we're going to be represented by a dot in what we call it Hough space here, okay? All right. Simply put, in the Hough space, I'm going to put here my m, which is the slope of the lines, of all lines. Here I'm going to put the b, which is again the intercept with the y-axis. And each of the line, again I mentioned, this line can be represented by y equal mx plus b. So it has specific slope and specific intercept with the y-axis, m node and b node. Simply put, I can take this and put it in the Hough space at just one dot. Again, this dot represents a straight line, which is m and b, okay? In the same fashion, I can represent in the Hough space, again using this equation, I can represent the exact same point using what we call it rho and theta parameters, or rho and theta values. all right? Again, why are you teaching me this? Why are we going from, like an image space, so we'll call it Hough space, okay? The whole idea is that I wanted kind of to scan my image space. That's the whole intuition, okay? I'm gonna show you all the details in the next slide. But the whole idea is I need to look for a line, okay? So in order to look for that line, what I'm gonna do, I'm gonna kind of scan the entire image in a way, and each time or each of the points, I will try to get, rho and theta for these different points. So along the point, along whatever points, I'm gonna get rho and theta. Again, rho and theta, or M and B all the time, okay? And I'm gonna draw that here in what we call it my Hough space. So simply in the Hough space, I'm gonna be drawing all the representing the entire image in what we call it M and B coordinates, or rho and theta coordinates, all right? And simply put, we're gonna do what we call kind of a voting exercise. In simple forms, every time you're gonna be doing, a transformation from an image space to a Hough space, you will see kind of the M and B has been repeated several times, which kind of a voting way, which is kind of an accumulator. It's kind of in this point, which is indicating M and B or rho and theta, you will see that there is kind of, like an accumulator that shows, okay, there's like 80 points, or let's say 100 points, which means that's kind of a vote that tells you, okay, maybe this point has a line in it when you shift from here back to the image space, okay? If it's not clear, I'm gonna show you an exact example moving forward, but that's the whole idea of why do we actually move from an image space to what we call it Hough space, okay? Simply put, I'm gonna represent every line in the image space by a dot in the Hough space, okay? Again, this dot can be M and B or can be rho and theta. Let's again take another look, an actual practical example. Let's assume that I have this image, which is again pure white image, with two lines, horizontal lines in it, a blue line and a yellow line, okay? And this image is 100 by 100 image with horizontal line in the middle. I try to include the details here as much as possible, again, to avoid any confusion. It's a little bit confusing at first, but once we run it, you will see it's very easy. First, we're gonna create what we call a 2D matrix. So we're gonna create a matrix, okay, that has all the rows and all the thetas, all right? Kind of all the rows here and all the thetas in here, okay? And we'll set it, all of it, to zeros. So simply put, we don't know where the line is. We're just gonna create a matrix and set 0 into it. All right, first step, I'm gonna select the first point on the line. So let's assume they're gonna select the first point here on that line, okay? So for each point, what I'm going to do is that I'm going to kind of scan the entire angles, entire theta, okay? So we're gonna do a rotation from, let's say, 0, 1, 2, and so on up until, let's say, 180, okay? So we're gonna try simply different values of theta, all right? And for each value, I'm gonna obtain the rho back again, all right? So again, simply put, here I have this equation. I know this point, so I know x and I know y. And what I'm gonna do is I'm gonna try different values of theta. I'm gonna try theta of 1. So here I have all the values here are known. However, rho is unknown. So basically, I'm gonna substitute in this equation, get rho value, all right? All right, which means at this point, I'm gonna get rho and theta, all right? I'm gonna put it here in this matrix, okay? And then the next step, what I'm gonna do is, for every rho and theta pair, what I'm gonna do is I'm gonna go, let's say, to the next point, all right? And do the exact same exercise again, and come again with rho and theta values. I'm gonna come to the next point as well, and do again the exact same exercise, rho and theta values. So you guys can see here, simply put, the rho and theta value, which is here, we're gonna be 50 and 90, all right? Again, it's a little bit confusing, but bear in mind, so bear with me. So 50 and 90 indicates that, okay, rho, which is again distance from the origin, it's in the center exactly. So here the distance is 50, and the angle is 90, right? Which is the angle from the origin to the line is 90 degrees. And that's why you will see in that specific cell, which is 50 and 90, okay, every time I'm gonna be incrementing it by 1, all right? So again, as you move forward, for example, this line, you will see that every time all the points here on the line have a 50 and 90 rho and theta, all right? All of these points have 50 and 90. Every time you draw a perpendicular line from the origin to that line, you're gonna get the exact same value. it's at the same distance 50 and have this exact same angle 90. Simply put, every time you're gonna move to this line, you're gonna kind of increase the accumulator within that value here by 1. So here you're increasing it by 1, 1, 1, 1, which means simply when you go to the Hough space, when you see a point in the Hough space that has a lot of values, the accumulator is very high, it's a very large number, that indicates that a line has been found in a very simple form, okay? All right? So simply put, this line is represented the Hough transform as just one dot, okay, indicating a lot of intersecting simply points, or a lot of accumulators, just kind of, you know, like a lot of values within that grid that we created out of zero, out of nothing, okay? So simply put, cell 50 and 90 will be voted up. The accumulator with maximum votes simply indicates a line. So a line has been indicated or detected in the image. All right, what about the yellow line? So this line has this exact same angle. So you guys can see that theta is the same, so 90 is the same. However, the distance from the origin is around, here we set it to 25, pretty much. Okay, so the distance from here to here is around 25. The distance from here to the blue line is 50. And that's why you would see here, if we have two lines, you would see that this accumulator has been accumulated as well, increased as well, indicating there's another line at 2590 location. Okay, again, it's kind of a different representation of the exact same thing in what we call it an Hough transform, as opposed to the image transform. Okay, all right. So what I'm gonna do with this, simply put, I'm gonna apply kind of, you know, like find Hough lines, okay, kind of the function we're going to be using within OpenCV that can gives me exactly what are the rho and thetas of all the lines that have been found in the image. It's really powerful, it's really intuitive, and it's going to be used to detect lane lines within an image. All right. Okay. So how can we apply it? I'm going to actually use again cv2.houghLines. I'm going to provide it with the image. I'm going to provide it with these parameters. I'm going to provide it with rho accuracy, theta accuracy, and threshold value. Simply put, here I'm going to define, in general, let's assume I'm going to put, let's say, 1 and pi divided by 180, which means 1 degrees, and then 240. That will kind of create our resolution, all right? So the resolution within the parameter rho, how many pixels I'm going to need my resolution within the parameter rho. I need theta, which is my resolution of how many angles I'm going to be doing. You guys remember we had a grid, okay? That indicates the grid here. How many times we're going to be evaluating and rotating every 1 degree, every 2 degrees, and so on. All right, and that's the kind of the values going to be doing rho, theta, and the threshold as well. Threshold, which is kind of, you know, the vote. If you guys remember, every time we increase the accumulator, that's kind of, you know, the vote. How many times do I need to include? If I put, let's say, 240, that's kind of the minimum vote that I need to detect. Okay, that's a line. That's a flag that tells me, okay, I found the line. That's kind of the minimum threshold that I need. Okay. All right, and simply put, cv2.houghLines will gonna give me or return all the lines that has been found in the image, which is amazing because now I can basically select which line is perfect. I can know the slope. I can then center my vehicle. I can do wonders with it moving forward after we detect the lines within the image. All right, and that's pretty much all I have for this section. I hope you guys enjoyed it. And now to the fun part, and actually implement it within the Python environment. And then afterwards, what we're going to do, we're going to combine the region of interest masking along with the Hough transformation to actually detect a lane line within an image. I hope you guys enjoyed it, and see you in the next section.